Hello, my dear students, and the rest of the learners. Welcome to part 6 of the 7-part series of tutorials for Computer Structured Programming Unit in C and Pascal. This is section 4 of 4 in the topic Program Development and Design. My name is JM, or you can simply call me EMELISWAP. In this tutorial, we are going to look at program design tools, which include the pseudocodes, the flowchart, structure charts, and decision tables. When we talk about program design tools, they are the tools that are used to depict an algorithm. In other words, these are the tools that you use to develop an algorithm that we discussed in part 3 in this series under the program design. And therefore, these tools that you can use to design your algorithm or develop your algorithm, which we said that an algorithm is a series of steps that you are going to follow in order to solve your problem, include pseudocodes, flowcharts, structure charts, decision tables, decision trees, amongst others. However, for the sake of this tutorial, we are going to use or to learn about the pseudocodes, the flowcharts, structure charts, and decision tables. Ordinarily, when you are designing a program, you just need to choose one of the design tools that is applicable to the problem that you want to solve. Therefore, you don't usually need to make use of several design tools when you are developing or coming up with an algorithm to solve a single program or a single problem. And therefore, in an ordinary situation, in the working environment, or generally for learning purposes, what you need to do is to master one of the design tools that is preferable to you as a programmer. If you decide to make use of pseudocodes, make use of pseudocodes. If you decide to specialize in designing your algorithm using flowcharts, that's okay. If you want to make use of structure charts, that's okay, or decision tables, or any other. However, certain design tools are applicable for developing algorithms for certain kind of problems, and also depending with what you want to have or to illustrate in your algorithm. And therefore, we are going to commence by looking at pseudocode. What is a pseudocode? A pseudocode, just as I said before in my previous presentations, I said that a pseudocode is simply a general and generalized set of English-like statements that you write in form of English. In other words, a pseudocode is a set of steps written in English-like set of statements that illustrate the flow of your problem or how you are going to solve your problem. So pseudocode is a set of statements written in close to English-like statements that show the flow of the instructions, how they are going to be executed to solve a given problem. And therefore, pseudocode is a generic way of describing an algorithm using the conventions of programming languages without using language-specific syntax. Pseudocode describes model design in ones using syntax like programming language. In other words, when you are developing an algorithm using the pseudocode, when you are writing down your set of steps in form of English-like statements, these statements can be general, can be near English, or they can be near the type of syntax that a certain programming language requires. And therefore, writing a pseudocode aims at providing programmers with clear and unambiguous process specifications. Process logic in pseudocode is expressed as a combination of sequence of events, decisions that need to be implemented, and actions that may have been repeated. Some of the ones used may be drawn directly from a programming language, just as I have said, and then mixed with English-like statements to form what we call structured statements that are easily understood by non-programmers and also make a lot of sense to programmers. In other words, when you are writing your algorithm, when you are outlining or listing the set of steps that you are going to follow in form of English-like statements, these statements can be making use of ones that are a little bit close to the type of language that you are going to use to code your program, or they can just be statements that are English-like. They are not related to any programming language, but they are simply outlining exact steps of what is going to be done. And therefore, depending on the writer, the pseudocode may vary widely in style, from a near exact imitation of a real programming language on one extreme, and on the other extreme, you can have a description that is approaching formatted prose at the other. Or in other ones, on one extreme, you can have just the set of statements that are going to be followed without adhering to any format of any programming language. While on the other extent, you can have an algorithm or a pseudocode whose syntax is almost close to the programming language that you are going to use during coding. The main applications of pseudocode are, number one, in computer science textbooks, mostly pseudocode is used to illustrate various examples or case scenarios because every programmer will understand the pseudocode, but not every programmer that will understand the same programming language. And therefore, because different programmers are specialists or are specialized in certain programming languages, when it comes to writing of books, instead of the writers limiting themselves or restricting themselves to making use of a certain programming language or a certain syntax, they just write down the algorithm in form of a pseudocode that can be understood by everyone. Secondly, a programmer who needs to implement a specific algorithm, especially an unfamiliar one, will often start with a pseudocode description and then simply translate that description into the target programming language and modify it to interact correctly with the rest of the program. The following are therefore some of the guidelines that you need to adhere to or abide to when you are writing a pseudocode. Number one, the statements must be short, clear, and readable. You don't write the paragraphs in a pseudocode. You just write simple, short, readable, and clear statements, as I am going to show you in this presentation. Secondly, the statements must not have more than one meaning. They should not be ambiguous. They should be clear, straightforward kind of statements that have only a single meaning, that every person who reads will be able to know exactly what is intended. Number three, the pseudocode lines should be clearly outlined and indented. In other words, the way you write the statements, they should clearly indicate their levels. For example, if you enter a certain value and then you check a certain condition, the path for the condition will be indented. I explained what is indentation as one of the qualities of a good program in my previous presentations within this series. And therefore, if you want to remind yourself about what indentation is, kindly refer to the previous parts in this series. Number 4, the other rule you need to adhere to is that your pseudocode should illustrate or show clearly the start and the step of executable statements and the control structures. In other words, your pseudocode should have a statement that indicates this is the starting point and another one that indicates the stop. So you can even use ones like start, do X, Y, Z. When you are through, stop. The next rule is that the input, output, and the processing statements should be clearly stated using keywords that are clear. For example, read, input, amongst the others. The following are therefore 2 examples that I have used to demonstrate to you, my dear students and the rest of the learners, how to write a pseudocode. The first one is a pseudocode for a program that requires the user to enter radius of a circle, then computes its area and perimeter and displays the results on the screen. Always, when you are writing your pseudocode, ensure that your pseudocode has an heading. It has a title. In this case, my title is calculating area and perimeter of a circle. So my pseudocode is nearer or is almost close to the language that I expect to use, which is Pascal in my presentations. And therefore, my first statement is to indicate the constants that I will require. In this case, I'll use pi. Then I will also indicate, or I'm also indicating the variables that I will use. In this case, I'll use a variable called radius and use R to represent radius. Then perimeter, P, and area, A. So those are the variables that I will require and the constant that I will require. And from there, I have start. Where do I start? What do I do? Number 1 is set my pi 3.143. Next is from the user for the radius. Then store that radius in a memory location called R. Then set the perimeter P, or calculate the perimeter by the formula using the formula 2 times pi times R. Then set area as pi times R times R. In other words, calculate the area of the circle by the formula or by multiplying the content in pi times what is entered as radius times that which is entered as radius. In other words, it is set pi or set area by R squared, pi times R times R. Then print P or display the value of perimeter. Then print A or display the area of the circle. And I stop. My dear students and the rest of the learners, you can see that in this pseudocode of mine, constants, variables, start and end and stop are within one line, while the rest of the statements are enclosed in between start and stop. So that's what we call indentation. To illustrate the various levels of your statements. And generally, we say that indenting is that arrangement of your sentences or your instructions within your code to indicate which statements are at the same level, which statements are doing what, and therefore it becomes easy. If, for example, you want a condition, you are entering a certain value, and then you are checking a condition, the section for condition can be indented, can be pushed inwards a little bit from the rest of the statements. The next pseudocode is a pseudocode for a program that prompts for the gross salary of an employee and calculates his or her salary, that is net salary, given that the income tax rate or tax rate is 14%. It then displays that employee's gross salary, amount taxed, and the net salary. A pseudocode for a program that prompts for the gross salary of an employee and calculates his or her net salary, given that the income tax rate is 14%. It then displays the employee's gross salary, the amount taxed, and the net salary. So as usual, my title for the pseudocode is calculating net salary. So what will I require? Number one is a constant to be used, that is the tax rate. In my pseudocode, I'm calling it or use the word rate. Then the variables that my program will require, and I'll use them in my pseudocode, is gross salary. I'll use the word gross to represent gross salary, tax to represent income tax, and net for net salary. And therefore, I'll require three variables for my program. One is gross, two is tax, three is net salary, that is net. Once I have done that, then I begin. One is I'll begin by setting the rate 0.14, that is 14%. Number two, or step two, I'll prompt the user for gross salary. Number three is to store the gross salary in gross. Number four is to set tax to rate times gross. Number five is set net to gross minus tax. Number six is display the gross salary, the tax, and the net salary. And that is my other algorithm, or this is my other pseudocode. As you can see, my dear students and the rest of the learners, is that this pseudocode is almost close to the program that they expect to use, the programming language that they expect to use, which is Pascal, that makes use of the word begin and end, as we are going to see in my subsequent presentations. The next tool that you can use is a flowchart. A flowchart is generally a diagrammatic representation of the statements or of the algorithm that I'm going to use. Diagrammatic representation of the flow or the sequence of execution of your instructions, the flow of your program. And therefore, a flowchart, a program flowchart, is used to describe the flow of data through a particular computer program, showing the exact sequence of operations to be performed by that program in order to process data. Different graphic symbols are used to present data input and output, decisions, branches, and subroutines. And therefore, these symbols are used to represent a well-defined sequence of activities. And therefore, a flowchart is used to represent any well-defined sequence of activities. It indicates the flow of the instructions, just as we have seen for the pseudocode. But then in this case, we use both the symbols and some short and brief statements, as you are going to see. Therefore, flowcharts are used to convey in a diagrammatic form the logic, the processing operations, and the flow of control that is required by a computer program. The flowcharts are used by programmers in two main ways. Number one, to plan the structure of a program before it is written, and number two, to describe the structure of a program after it has been written. Unlike pseudocode, which expresses ideas in form of short statements, a flowchart does the same, using both statements and special symbols that have specific meaning. So in other words, Whereas in pseudocode, we just use short statements that are written in English-like form. For a flowchart, we combine those short statements, but then we also include a symbol that illustrates the kind of operation that is being carried out. Some common symbols that are used to draw program flowchart is, number one, we have this symbol. This symbol that we use is called an ellipse, or usually we call it a terminator. A terminator denotes the beginning and the end of the program algorithm. And therefore, any flowchart that I'm going to use or that I'm going to draw is supposed to have a terminator at the beginning of the flowchart and at the end of the flowchart. This other symbol that we use is called a parallelogram. A parallelogram is used to denote an input or output operation. Therefore, any point where the program or the processor will be required to read a certain value or display a certain value, we are going to use the parallelogram. So it is used to indicate or denote an input operation or an output operation. For example, using the ones read, print, write, amongst others. Then we have this other symbol that we call a rectangle. It is used to indicate that a processing activity or data transformation is taking place. There is a calculation taking place or some computations being done. For example, sum equals to A plus B. So this is a computation operation. And therefore, we use a rectangle. Then we have this other symbol. This symbol, we call it a robust. It is used to specify a condition. It is a diamond shape that shows where a decision or a test is to be made between two alternatives. And therefore, if you have a condition, for example, you have entered the age of a person, and then based on the age, you are saying that if the age entered is beyond 18, then do X. However, if the age entered is below 18, then do another action, like do activity Z. So in that case, you are checking. There is a condition that is being checked. So whenever there is a condition to be checked so that an alternative is taken or a certain action is taken, we make use of a robust. And therefore, robust is used to specify a condition. Then we have this other symbol. This symbol, we call it a connector. It is used as a connecting point or interface for arrows showing or coming from different directions. So if you have several alternatives being taken within your flowchart and you have several paths or routes to follow, at the end of the day, they should be connected together before you exit the program, or you may have a program that has several paths or alternatives, for example, using a condition, but at the end of the day, regardless of the route or condition that will be met, there will be other actions to be taken next that are common. And therefore, you need to use a connector to connect the different paths together. You connect the arrows together or using a connector so that then you can be able to have a common flow next or next step. Or before you exit a program, you are supposed to connect those paths together first, and then you exit or you terminate the program. And therefore, we use a connector. A connector can also be used in a situation where you are drawing a flowchart and it is not fitting within the same page. So whichever path, whichever arrow that you have in the previous page, you use a connector to indicate that you are going to continue next page. If you have several paths, for example, 3, on the page you are terminating, you use 3 connectors. On the page where the flowchart is continuing, you still use the connectors to link the pathways or to link the paths. And then we have this other symbol here, call it an arrow. It is used to indicate the direction of flow of program logic. And therefore, those are the main symbols that we use. The flowcharts are useful when programming because they allow the programmer to set out in a simple way a sequence that he or she wants for each line of the program. The following are the main guidelines for drawing a flowchart, or main rules that you are supposed to adhere to when writing a flowchart or drawing a flowchart. Number one, there should be only one entry with the terminator or starting point and one exit point of the program algorithm. Number one, so you should have a single start and a single stop, a single begin and a single end. Number two, use the correct symbols at each stage in the flowchart because each symbol illustrates a specific type of operation. Number three, the logical flow should be clearly shown using arrows. Number four, try to keep logic flow from the top to bottom and from right to left. Don't have lines crisscrossing all over. Don't have arrows passing over each other. Then use connectors to reduce the number of flow lines. The next rule is that always add notes if necessary, but don't clutter the diagram. Number seven, the lines should ideally be vertical or horizontal. So avoid crossed flow of lines. And that's what I've already said. Don't have arrows crisscrossing each other. Number eight, be as neat and tidy as possible when you are drawing a flowchart. What are the main advantages of using a flowchart? Number one, they give the programmer good visual reference of what the program will do. Secondly, they serve as a program or system documentation. Thirdly, it is easy to trace through from the start to the end to find the action resulting from a set of conditions. Number four, they allow programmers to test alternative solutions to a problem without overcoding the program. However, flowcharts also have certain limitations or certain disadvantages. One of them is that there are so many different ways to draw flowcharts. So there is no common way of drawing, though the symbols are the same. Number two, it is difficult to remain neat and uncluttered if the logic is complex. Number three, constructing a flowchart is time consuming. Number four, they take up considerable space. Number five, they are difficult to amend without redrawing. So in case you make any change, you are supposed or you might be forced to redraw the entire flowchart. The following are therefore some examples of flowcharts that I want to use or which I am using to illustrate how to draw or design a pseudocode or how to design an algorithm using a flowchart. In this case, I'll just convert the pseudocodes that I've already demonstrated and I replace them with their respective flowcharts. And therefore, my first flowchart is a flowchart for a program that requests the user to enter radius of a circle, then computes its area and perimeter and displays the results on the screen. The second one is a flowchart for a program that prompts for the gross salary of an employee and calculates his or her net salary, given that the income tax rate is 14%. It then displays that employee's gross salary, the amount taxed, and the net salary. So we begin with a flowchart that requests the user to enter radius of a circle, then computes its area and perimeter, and displays the results on the screen. As usual, your flowchart must always have a title or a heading. So my heading is calculating and displaying perimeter and area of a circle. And this is my flowchart. We have the start and the stop using the terminator. And then the next step is to assign 3.143 to pi. And you can see that operation is in a rectangle. Then input R, read value R, read radius. And that symbol there is the parallelogram because the operation of reading radius is an input operation. And then the next set of operations are for calculating the perimeter and the area. So P equals to 2 times pi times R. Area equals to pi times R times R. And therefore, because those two are computations, you are computing perimeter and computing area, we are using the symbol rectangle for processing. Then we display perimeter and display the area. So we use the parallelogram because that's an output operation. We are outputting perimeter and outputting the area A. And then that becomes the end of that operation, that algorithm. And therefore, we stop. Good. The next is a flowchart for the program that prompts for gross salary of an employee, then it computes his or her net salary, given the tax rate at 14%, and then displays the gross salary, the amount taxed, and the net salary. And here we have, of course, the title. The title of this flowchart is calculating net salary based on gross salary and tax. And therefore, that's it. We have the begin and the end using terminators. After begin, the next thing we do is to get tax rate. We assign 0.14 rate. And then we declare, we set aside memory locations for tax, for gross, and for net. Then we have input operation. We are reading gross salary. So inputting gross. And the symbol there is for input. That is input operation symbol, which is parallelogram. Once you have gotten the gross, the next step is to compute the tax and compute the net salary. The computation of the formula for calculating tax is rate times gross, or for computing net is gross minus tax. So those two are processing operations. They are computation or they are calculation or they are calculating operations. They are computing operations, processing operations. And therefore, because we are calculating tax and net, we use the symbol for processing, that is rectangle. And then we display gross, tax, and net. We output in gross, tax, and net. Therefore, the symbol we use is a parallelogram, which is used for both input, as you have seen, is the one which you have used for gross, inputting gross, and the same one we are using for outputting the gross salary, the tax, and the net of them. So we use a parallelogram for output. And we end. So begin, end, all operations, all the activities are being carried out in between begin and end. The other tool that you can decide to use to design your algorithm is the structure chart. Structured charts show the overall framework of the program, with each level showing progressively more detail. The program is separated into modules, one for each main function. Modules are developed starting from top and moving down the hierarchy. This method ensures that all modules link in together as the program develops. Structure charts are used mainly to show relationships between program modules and graphically depicts the breakdown of modules. It is often used with other design tools, such as pseudocodes and flowcharts, to express the process or procedure logic. The following is an example of the design of exam results using a structure chart. So here, my dear students and the rest of the learners, I have broken down a problem of tabulating students' results in form of its structure, how it is structured, how it is modularized. So the overall function of my program is tabulating students' results. And therefore, the overall function in this case is results tabulate. Then this function is broken down into three major functions or major modules. One for inputting details. I am calling it input details. The next is to process what has been entered, so processing details. And then we display the results or give out the results through the function that I'm calling int report. The module or the function for inputting details is further broken down into two submodules or subfunctions, which are one, validating input, the other one is editing the input. For the processing of details function, it is broken down into four subfunctions. One is for calculating the subject total. The other one is for calculating student mean score. The other one is for calculating mean grade. The other one is for calculating comments. For example, finding whether the student is a distinction, a credit, or a pass, or a fail. And therefore, that's how we break it down. Each function is performing a specific task. I will explain about the functions and the rules of functions in my subsequent presentations in this series. Then the function for printing a report is broken down further into a subfunction for printing total, marks, printing mean score, printing mean grade, and generating comment. Lastly, that function or subfunction for validating input is broken down further to another subfunction that we call print errors. So this is a structure. It illustrates how the major function or the program is broken down into modules. So these are simple, in simple manner, in simple language, these are modules. How are the modules structured? Which is at the highest level and which is at the bottom level or the lowest level. The last tool that I'm going to illustrate is what we call the decision tables. These are precise yet compact way to model complicated logic. They associate conditions with actions to perform, but in many cases, they do so in a more elegant way. It has four quadrants. These four quadrants are conditions quadrant, the conditions alternatives quadrant, the actions quadrant, and the action entries quadrant. Each decision corresponds to a variable, a relation, or a predicate whose possible values are listed among the condition alternatives. Each action is a procedure or operation to perform, and the entries specify whether or they specify the order with which an action is to be performed for the set of condition alternatives that the entry corresponds to. Each action is a procedure or operation to perform, and the entries specify the order in which each action is to be performed for the set of condition alternatives that the entry corresponds to. Many decision tables include in their condition alternatives the don't care symbol or hyphen. Using don't cares can simplify decision tables, especially when a given condition has little influence on the actions performed. In some cases, entire conditions thought to be important initially may be found to be irrelevant when none of the conditions influence which actions are performed. As part or apart from the basic four quadrants structure, therefore, decision tables vary widely in the way the condition alternatives and the action entries are represented. Some decision tables use simple true-false values to represent the alternatives to a condition akin to if then else. Other tables may use numbered alternatives akin to switch case. And some tables may even use fuzzy language or fuzzy logic or probabilistic representations for condition alternatives. In a similar way, action entries can simply represent whether an action is to be performed, that they check the actions to be performed, or in more advanced decision tables, the sequencing of actions to perform, that is the number of actions to perform. The benefits for using decision tables include, number one, decision tables allow developers and the policy experts to work from the same information, that is, to work from the decision table itself. Secondly, decision tables render nested if statements from traditional programming languages into decision tables that can be used as a debugging tool. That is, decision tables are tools to render nested if statements from traditional programming languages into decision tables, and they can be used as debugging tools. Number 3, decision tables have proven to be easier to understand and review than the code, and have even been used extensively and successfully to produce specifications for complex systems. The following are the steps that you need to follow to develop a decision table. Number 1, you should figure out the most essential factors to be considered in making a decision. This will help identify the conditions involved in the decision. Only those conditions should be selected which have the potential to either occur or not, but partial occurrences are not permissible. Number 2, determine the most possible steps that can take place under varying conditions and not just under current conditions. This step will identify the actions. Number 3, calculate all the possible combinations of conditions. For every number of conditions, there are always a number of combinations to be considered. Therefore, you should consider all the available combinations or alternatives based on each condition. Therefore, because you may have several conditions, ensure you also cater for they have several combinations. Number 4, fill the decision rules in the table. Entries in a decision table are filled as Y or N, and action entries are generally marked as X. For the conditions that are immaterial, a hyphen is generally put. Decision table is further simplified by eliminating and consolidating certain rules. Impossible rules are eliminated. There are certain conditions whose values do not affect the decision and always result in the same action. Such rules can be consolidated in a single rule. The following is therefore a decision table demonstrating how decision tables can scale several conditions with many possibilities. In this example that I'm going to show you, my dear students, the rest of the learners, is for a decision table that is used to diagnose printer problems based upon symptoms described through a phone by customers. As usual, you should have the heading for your table. In this case, my heading is Unbalanced Decision Table for Troubleshooting a Printer. So here is our decision table. It has conditions, it has rules, it has actions to be carried out. I would like you to look at each of these conditions, the rules in place, and the actions to be taken. For example, if the condition is that a printer does not print, what happens? Do you check the power cable? Do you check the printer computer cable? Do you ensure that the printer software is installed? Do you ensure that you check or replace the ink? Do you ensure that you check for paper jam? What about if a red light is flashing? What do you do? What rule should you adhere to? Which rules must you abide to? And after you adhere to a certain rule, what action should you take? And with that, my dear students and the rest of the learners, we have come to the end of this topic on program development and design. And this is the last part in the 4-part series of tutorials on program development and design. Congratulations for learning section 4 of the topic program development and design. You can also access section 1 to 3 of this topic, other topics in the computer structured programming unit, as well as other computer or ICT videos by clicking or tapping on EMELISWAP ICT YouTube channel below this video. You can also visit EMELISWAP Life Skills YouTube channel for free life skills, motivational, and inspirational resources. To subscribe to the channel, tap on subscribe button below this video in YouTube if it's not currently reading as subscribed. For any further correspondence, kindly write it to us through the email emeliswap@gmail.com. Thank you very much for listening to me, and let's meet in part 7 of the series. God bless.